We're going to talk more about electron spins today. This picture here is indicating what happens when you put an electron, or actually any particle with spin, in a strong magnetic field. So the magnetic field direction we, by default, define as the z direction. And you will only have a portion of the magnetic or the angular momentum that's parallel to that magnetic field. And then it goes around or precesses, like a top precesses, or the Earth precesses. It's on the order of, I think, 13,000 years or something. I don't remember the precession rate for the Earth. It's very long. And so it's going to precess. And we'll see more theory on that coming up. So that picture is related to what we're going to talk about. But first, we're going to start by taking lone electrons. So today's lecture is going to be completely outside of the hydrogen atom. Just saying, what if we have a bare electron? Well, if we have a bare electron, and then we say, okay, so what's its Hamiltonian? That bare electron's potential energy is just going to be based on its magnetic, a bare electron in a magnetic field. I should have said in a magnetic field. So if it's in a magnetic field, then it's going to have potential energy due to the magnetic field. And remember, I said we can't really make a Schrodinger equation for spin because it's an innate property. But we have the potential energy, we have a function for that. So the potential energy is minus mu, which is the magnetic moment. So that's the magnetic moment of the particle dotted with the external magnetic field. So as we saw from last class period, we used gamma to be the gyromagnetic ratio. Magnetic, believe me, that's magnetic. The gyromagnetic ratio that tells you the relationship between the angular momentum and the magnetic moment. And so magnetic moment is the gyromagnetic ratio times the angular momentum by definition, dotted with B. And then we said by definition, the z direction is the direction of the external magnetic field. So when I'm doing a dot product of S vector with B vector, the part that's parallel to B is S sub z, and so the dot product just simply becomes S sub z times B0, the strength of that external magnetic field. So we conveniently get rid of the dot product, and now putting in the Pauli matrix, H bar over 2 times the Pauli matrix, we have that our Hamiltonian for this potential energy is this matrix. We can find eigenvalues. Remember, H times, I'll put chi equals E chi, right? So how do we find the eigenvalues?
So we do the determinant, the determinant of a bar minus E times I equals 0.
Excellent. So I'm just gamma B0 H bar over 2. Well, let's make life simple. Let's make life really simple. We don't need to do all this work because our matrix is diagonalized. So I could rewrite the matrix as minus gamma B0 H bar over 2, 0, 0, gamma B0 H bar over 2. Notice there was a minus sign out front, which is why this term here became negative. and the one that had the negative sign became positive. And so we have our two eigenvalues are minus and plus, because that's our H matrix. And if we actually wanted to go through with our formalism, we'd say the stuff I have written minus lambda, okay. We would do the determinant of this equals 0, and all we would have is we'd have this equation, which is true if this thing is 0 or this thing is 0, which means lambda is equal to one of those two values, right? That's why we can just read it.
Right.
And so that's where we get the two energy eigenvalues. Notice E plus minus is equal to plus minus and then inside the minus sign. Or it could have been written, I wrote this, so I could have written it more succinctly, but possibly with less clarity, like this. The minus plus, that just indicates you're flipping the sign, but I wanted you to see why you had the flip of the sign, so that's why I didn't do it.
Question.
Yes?
Actually, never mind. No question. Actually, I'm still going to ask it. It's probably a dumb question, but I'm just going to ask it. For our energy being plus minus, what is the significance of having the negative? I mean, obviously we can tell from the math that there's going to be a negative, but what is the significance in having the flip for the signs between the energy and the eigenvalue?
I would have to go back to some of the derivation, but I believe it is this. If your magnetic field is aligned with the angular momentum, because you have a negative charge, that means your magnetic moment is anti-aligned. And that would give you a higher energy state. And the opposite of them would be a lower energy state. And so I believe that's where it comes from. That's why it's reversed, because the charge reverses the direction. Okay, now, previously we showed that with the time-dependent Schrodinger equation, we could separate out the time part from the spatial part. We're going to do this, well, we're going to apply the same idea to say that we could separate out the time part from the spin up, spin down part. And so we could say that our wave function for spins, this is our spin wave function, is equal to some constant times spin up times e to the minus I, e for spin up, t over h bar, plus a second constant times the spin down state, e to the minus e for the spin down state time over h bar. Well, of course, the e plus is minus and the e minus is plus. So you see that the signs out here are flipped because of e minus being positive and e positive being minus. But otherwise, the exponents are the same. And because the spinors are chi plus is equal to 1, 0, and chi minus equals 0, 1, then we can combine these two equations into its own eigenstate that is just a vector with the thing that was multiplied by the plus spinor on top, thing that was multiplied by the minus spinor on bottom. Does that all make sense? I mean, it's probably not what you would have thought to do, and you probably aren't seeing where this is leading, but it makes logical sense.
Yeah.
So how is this useful to us? what's the expectation value for the spin in the x direction? If I'm going to find the expectation value, then I have to put, perfect. I don't know why it's doing that. There. I have to put my chi-state, Sx chi-state. And so I put, remember, chi is, exponent is positive I for the A term and negative I for the B term. So that means, and this is something that I think we had a problem with on the last test, so I'm going to do it very specifically. Not beta B. I hate it when I have my phone in my pocket and it's ringing, as is happening right now. So that's what ket chi is. So bra chi is, you do the transpose, so it's going to be flipped to a row vector instead of a column vector, and you do the complex conjugate. So technically it's A star e to the minus I gamma B0 t over 2, B star e to the I gamma B0 t over 2. Now I said technically because we probably would have chosen A and B to be reals, but we didn't have to. So you notice in my work I did choose them to be reals. So this here is the chi star, or the bra for the chi. And then I have my Sx vector, and then the ket chi. Now to multiply these, I always do multiply one first, then the other. I can't do all of them in one step. Maybe I'm not smart enough, or I always reject that out of hand, but I have to offer it as an option. So let's do the multiplication. So I'm going to do the first multiplication, then leave the second vector in place. So I'm going to have h bar over 2, and then a times 0 is 0, b times 1 is 1, then go down to the lower one, a times 1 is 1, and then b times 0 is 0, and oh, it's column. And then multiply it by this vector. And of course, I had exactly that written out, right? That's what this next line is, but just showing the process. Of course, I didn't show specifically this times this plus this times this, but I said it. So now we just have to multiply these. We're going to have a times b. Both of these have the same exponent. And so when I multiply the first term, I'm going to get notice the over 2 disappears because I had e to the I gamma b0 t over 2 times e to the I gamma b 0t over 2. And so I have that for my first term, and then my second term will be that. Once again, they both have a minus exponent, so that's why it's minus. Or h bar over 2 ab times e to the I gamma b0t plus e to the minus I gamma b0t. That's 2 cosine of gamma b0t. Using the definition that so I have a function, the magnetic field in the, the twos are going to cancel. I was like, oh, I've got a 2 factor off again. No, I don't. So I'm going to have my x component varies as cosine. If I do for the y component, I just change it from the, of course, s sub x to s sub y, which introduces the i's and the opposite sign for the i's. And so that's going to give me, without going through all the work, you can see it's going to be very symmetrical. You just have i's in front of each term and a minus sign in front of that second one. And so you have a minus ab h over 2i e to this stuff. Well, if I move this 2i to over here, that's sine, exactly. And so I have minus ABH bar sine of gamma B0T. So my SX my SY and what this is, oops, I's disappeared because the I goes into that. I was like, whoops, I got a mistake with that I. Keep in mind what we generally do. If I have a circle and I define an angle theta here, then I would have the x component the y component this looks a lot the same. It looks a lot the same with the change that, come on, R is ABH bar, and I have a minus sign here instead of a plus sign. What does that indicate? It simply indicates that my angle is in the opposite direction. Because if you change the direction for your angle, if I put it in the negative angle, it would change the sign of the sine term, but not the cosine term.
Right.
So putting that together, since I have my angle is proportional to time, I apparently have there I've explicitly put minus omega t in there so that I get the plus sign outside of the sign. And what is omega then? And of course, I put a minus sign in here because that indicates direction. The omega is still the positive value, just to make sure that my sign was only to indicate direction, right? To make sure we're clear on what the direction was. There was, for instance, no minus sign up here. So we have a frequency at which it's going to be precessing now because my magnetic field in the XY plane is going in a circle. The Z direction is staying constant and the X direction is precessing. XY direction is precessing. And so this frequency, omega, where do I have it? Yeah, I thought I had it right there, but no, I have it here. This omega is called the Larmor frequency, the frequency of precession. And so we will see how that works in a second. I forgot to look at this as I was going through. The SZ value is going to be going through all the same work, but now with our diagonalized matrix, it's just going to be h bar over 2 times a squared minus b squared, because you're going to have one positive exponent, one a negative exponent. You multiply them together, it's e to the 0 because of the position here. And likewise, these two here will give me exponent of 0. This minus sign is why there's a minus sign between the two.
Right.
So the SZ is constant, but the XY is precessing around. Hence the picture that we started with. The vertical component is constant, but the XY is precessing. The total angular momentum, just to finish things up, what's the total angular momentum going to be doing? It better be staying constant. If it's not, we've really messed something up, because what's the total angular momentum always for an electron? Always. This is s squared. For an electron, that's always true. So if I didn't get that, I'd have a major mistake. I'd be something that's always true isn't true. And so in this case, of course, the matrix is the easiest matrix to do any work with. And my work here is done. Now I have nuclear magnetic resonance. Have you guys done this like in organic chemistry? Nope. Medical procedure?
Never even heard of this before.
Really? Okay.
Yeah.
Well,
I've been trying to get research on this over the summer.
okay, so one of you hasn't. Well, NMR, back when I was a youngster, this, I think, first was introduced into the hospital setting. Nuclear magnetic resonance imaging, NMR. You would go in and they would put you in this tube and you come out an hour later and they'd have a high resolution picture of your insides. In my case, I had it done to my knee because I hurt my knee playing football, because, you know, football. People got really scared because it has nuclear. And we had things like, you know, Chernobyl went boom. There was the nuclear waste from the Love Canal and 3 Mile Island. People were very concerned about nuclear things. And so they saw nuclear and they're like, I'm not having an NMR. That's nuclear. That's dangerous. And so medical professionals said, well, that's ridiculous. Maybe they don't realize that their body has a lot of atoms in it, and each atom has a nucleus. And we're looking at the nuclei of all of those atoms in their body. So they simply changed the name from NMR. Let's drop off the N. Sometimes they'll write it like this. And let's emphasize the imaging part. So MRIs is what we call them now. So when I had the procedure done on my knee, it was an MRI. It wasn't an NMR. And then people aren't scared. Oh, magnets are safe.
One word.
Yes, indeed. What they're doing is they are putting you in a very strong magnetic field. They're putting you in a very strong magnetic field so that the nuclei, and I think they focus on hydrogen nuclei, will be precessing with a fairly high Larmor frequency. Remember, omega is equal to gamma B0. So the higher B0, the higher the frequency. So they put you in that strong magnetic field to get a high frequency, And then they send an electromagnetic wave, a radio wave, that's tuned to this frequency, and they measure how much is absorbed. And they say, there was this much hydrogen on this line, this much hydrogen on this line. And they take a whole bunch of lines, and then using computers, it's a very complex matrix algebra problem, really. They determine how much hydrogen was in each location in a very fine grid through your body. And so they're able to map out where the hydrogen is. So that's what NMR is doing. It's using what we've seen here. We did our calculation for electrons all by themselves. For the NMR, I'm pretty sure they're doing it for hydrogen. They're looking at the nuclear, so they're not worried about the electron spin. It's going to be a different frequency. They're looking for the nuclear spin, and it gives you a high resolution image. If you were in organic chemistry, they broaden it. They say any nucleus that has an odd number, that was the wrong one, odd number of protons and or neutrons will have a magnetic moment. So for instance, carbon 12, no dice. Carbon 13, we have 7 neutrons, we're good to go. So we can use NMR for any nucleus that has an odd number of protons and or neutrons. And you're going to get different results based on your spin state. This experiment, well, you probably didn't notice. I had it on this slide because I actually showed it in my general physics class just before this. How do we know that anything I've told you about spin of an electron is true? I know you have a lot of faith in me. I've never made a mistake, clearly. How do you know this is true?
Well, because it reacts to different fields, like a magnetic field, for instance. So
okay.
There has to be some sort of value or how you say, characteristic of the electron that makes it react to that field.
That's a very good answer. That's how they got started. They said, wow, we put a magnetic field and we see this. Or even the spin-orbit coupling, even not in a magnetic field, we see that fine structure. That means the electron must be behaving something like a magnet. And so there was a good reason to believe that the electron's behaving like it has a magnetic moment. So that's a good, the reason to believe is a good reason to believe it's true, right? Another example is the NMR I just talked about. We have all of this theory that makes a prediction. Then we go and we test and we see, does it absorb at the Larmor frequency? If not, then we've got ourselves an issue. We weren't right. But it does, so we have experimental evidence to back up the theory. Once again, the theory is not based on firm fundamentals, but it does make good predictions that we can then test. And that's why we have confidence in the quantum physics, because it makes predictions we can test and they turn out to be correct. Now, the Stern-Gerlach experiment is one of those really important experiments to illustrate that electrons have quantized spin orientation, that it can only be spin up, spin down, no matter what direction you choose to put your external magnetic field. So the Stern-Gerlach experiment is illustrated here. You have a region that has a magnetic field gradient. The magnetic field is changing in strength. That's actually important. If you want to look at a magnetic interaction, you will have a torque if you have a magnet in a magnetic field, but not a net force, just a torque. But with the changing magnetic field, then, well, actually, I didn't quite say that right, but let's move on. With the changing magnetic field, with the magnetic field gradient, you're going to have a force that's going to be making then the particle accelerate. And so what Stern and Gerlach did is they said, let's just shoot a beam of I'm going to say electrons here. I'm actually pretty sure it was like silver ions, but a beam of particles, actually it says atom beam, so goes along with the silver ions. Let's shoot those particles through the magnetic field. And if the orientation of the magnetic moment is uniformly distributed, then we should see the electrons striking. Okay, that was a bad. We should see electrons striking so that they fill this entire area, because some were aligned with the magnetic field, went one direction. Some were aligned against it, went the other direction. Some were somewhere in between. And so they're going to go somewhere in between because they didn't have as strong a force because of their alignment. So that would be the classical prediction as shown here. But what they found was there are only two traces, one on top, one on bottom, corresponding with only two possible orientations for their spin, what we call spin up and spin down. So that's an experimental measurement to show that this stuff isn't purely hypothetical. It's, once again, really there are only two orientations, and none of them are aligned, which makes so little sense. I don't know if you read the textbook where he talks about this. I like when he says, you're not getting the point, but that's probably not the best way to speak to your students. Spin addition. When I have two electrons. So once again, we're not talking about hydrogen atom, because the hydrogen atom is one if it's neutral. If I have two electrons and I combine them, there are four logical ways the electron spins could combine. You could have them both up, the first one up, the second one down, the second one down, the first one up. I said, nope, that was the same state. First one down, second one up, or both of them down. There are only four fundamental ways that the spins could be combined. And now I have a question. What's the total spin angular momentum in these? And how about the spin in the z direction? What would you say is the total angular momentum in that case?
Well, it's 2 times one of them.
Okay, so each one's 1/2.
Yeah, so I guess it'll just be 1.
So that would be a total spin of 1. What about this one?
-1.
Okay, now the total spin is only a positive value. So this would be 1 again. Remember, the orientation can go from -L to +L. So if it's total, if the orientation is -1, then the total must be +1.
Okay.
So what about these two in the middle?
0 then, since their orientations are opposites.
Okay, I'm going to put 0. We're going to find that's not correct. But I'm going to put that because that's the obvious answer. Now, if we talk about the z direction is the numbers that you said. 1, -1, and 0. So this is SZ. And up here, S for total spin.
So the top one, so for the ones in the middle, the total spin would also be 1 because it's not talking about the orientation, it's still just a total.
What we have here is a degeneracy. We have degeneracy because we have two states with SZ is 0. And so what we're going to do is we're going to make a superposition state of both of those. We're actually going to make two of them that have to be orthogonal to each other. And one of them will be S equals 1 and one will be S equals 0. That's where I said we're going to find out it's wrong. One will be S equals 1, one is S equals 0. Before doing the work, you don't know which. I mean, maybe you're smart enough that you do, but traditionally you don't know which one is which. But we're going to work through this then. And that's the key of this problem is what happens when we combine two particles with spin? How do we differentiate? How do we go forward? So first thing is defining the total spin and the total angular momentum operators. So the total spin, I said total spin, total angular momentum. That was wrong. The total angular momentum and the angular momentum in the z direction operators. So the total angular momentum in the z direction is just angular momentum of one plus angular momentum of the other in the z direction. That one's pretty straightforward. The total angular momentum vector is going to be the angular momentum of one vector plus angular momentum of the other one vector. It looks simple. Well, let's go through and do the work.
Okay.
We're going to define the state of both electrons as a ket up up, ket up down, ket down up, ket down down. That's just nomenclature. So if I want to find SZ, I'm just going to do SZ1 and SZ2. This superscript 1 means it's only acting on 1. Superscript 2, it's only acting on 2. Because they're two different particles, the SZ1 has no effect on particle 2, only on particle 1. And so just using the rules for the angular momentum in the z direction. Did you have a question?
No, I was just wondering if you meant M2 on the second term.
Yeah.
Yes, I did. You were just ahead of me there. Yes. I got it right here. Should count for something. You know I copy and paste a lot, right? So on the first particle, our eigenvector eigenvalue equation says that it's h bar m1 times chi1 and chi2. Second one, h bar m2 times chi1, chi2. And so the total angular momentum z direction is indeed just m1 plus m2. So what we did here was exactly right for the s sub z's. 1, 0, and minus 1. So 1, 0, 0, minus 1. That was easy. For the S total angular momentum, it's more complicated. And we come back to the raising lowering operator. I had to rewrite this because of my mistake last class period. This is what I should have had written. Instead, where I had S sub x, I think, the eigenvalues for S sub x. This is the exact and complete eigenvalue result for a raising and lowering operator. So let's test this real quick to see what value we get. So let's say S plus on up spin. We know what that should be. What should that give me? Indy answered this last class period. That's how I know we know the answer.
0.
Should be 0. So let's test and see if that's what we get. So what is the S value always for an electron?
1/2. Yeah.
So we have 1/2 times 3/2 is, well, I'll write it out. This is spin up, so M is 1/2. And because it's an S plus, it's going to be 3/2. 1/2 times 3/2 minus 1/2 times 3/2.
Very nice.
I forgot to put my H bar. I've got to be. Okay, so it's 0. Muy bueno. It's what it's supposed to be. First part is always going to be 1/2 times 3/2 minus, and now I have a spin down, so it's minus 1/2. Minus 1/2 plus 1/2 is, or plus 1 is plus 1/2. So that's going to be 3/4 minus a negative, so plus 1/4. 3/4 and 1/4 is 1. Oh, and it flips the spin. Because it is the raising operator after all. So S plus on the down operator is H bar, or S plus on the down eigenstate is H bar and the up state. S minus on the up state, what's that going to give me? Fill in the blanks.
So 1/2 times 2 halves. One half. Times -1/2.
That's right. Because of the plus or minus right there. And that's the lowering operator, so it's with the down equals, actually, I put an up here, but you can't raise the up, so it's good that it was 0. So 3/4 minus a negative, so plus a quarter is 1 again. And there, I did that one really quickly. An undefined state. As if that state exists. But minus times minus is a plus. 3/4 minus 3/4 is 0. So that's what I should have had last class period, where I had the mistake. The mistake, they had 2 mistakes because it had H bar over 2, and it had, what was the other part? Oh, one of them had a minus sign. Notice there's no minus signs here. So how is that raising / lowering operator going to help me? First, I'm going to calculate what happens when I put the raising operator on each state, because I should be able to take, well, not on each state, on the lowest state. I should be able to take this state here, we know L equals 1, right? That's L equals 1, M sub L equals -1. So if I take the L equals 1 state and I raise using the raising operator, that only changes the orientation. It didn't change the total angular momentum. So if I raise that, I'm going to still be in, I put L and M sub L. I am having a bad day. S and M sub S. So if I use the raising operator, it's going to change M sub S to 0, but S will stay at 1. And so that will tell me which state and what it exactly is I get for my middle state that is an S equals 1. And then I'll find what's orthogonal to that for my S equals 0 state. So if I do that, the raising operator on down, raising operator down, is going to raise the first one and give me the eigenvalue of H bar. Raise the second one and give me the eigenvalue of H bar. And so factor out the H bar, and that's H bar times up, down, plus down, up. That's a symmetric solution, right? So it's a symmetric solution. It's not normalized. How do I normalize it? I'm writing this in a convoluted manner. And something just, there we go. Stop responding there for a second. When you do this, you're going to get two h bar a mod squared. And so it turns out that a must be equal to 1 over the square root of there should have been another h bar here, actually. It doesn't really matter. So that I have my state is 1 over root 2 up, down, plus down, up. That's my normalized eigenstate. So that we call that 1, 0 because it's s equals 1, m sub s equals 0. So we got that state by using the raising operator on s equals 1, m sub s equals minus 1, and knowing that the raising operator cannot change the s, only the m sub s. If you raise it once more, and this is just for completeness, you will get 2h bar squared up, up, which tells us that up, up is the m sub s equals 1 for s equals 1, which we already knew. Is that what you're going to say with your but? But we already knew that?
Yes.
So there we found that we have 3 states, hence we call it a triplet state, 3 states for s equals 1. And then we'll have 1 state, so we'll call it a singlet state for s equals 0. What is that singlet state? Well, it has to be orthogonal to the triplet state that was a superposition. So it has to be a superposition again of these two, but it has to be orthogonal. How do you make it orthogonal? You switch up the signs. Right, so that way if you do 1, 0, bra 1, 0, ket 0, 1, you're going to have 1/2 times 1 minus 1 because of the change in sign. So that's the singlet state. So here's the summary of the triplet states and the singlet state. And we are, well, actually, the clock says we've been in class for 50 minutes, and the clock over there says I got 1.5 minutes left.
Yeah, they was started early, so we're good. Yeah. Our clock says you have 3 minutes, so that's probably it.
Good call. All right, now we're going to do some really fun stuff. This is like the last 3 slides. We said the triplet states all have a spin of 1. If this is true, then the spin squared operator in each one should be the same. So we're going to go ahead and check the spin squared operator in each one. And that's where life gets interesting. The fact that S plus shouldn't have changed it is good reason to believe it. But then this is doing the math to check it. And so the S squared is, of course, just S dot S. And so now we're doing the dot product between these, which gives us this plus 2 cross terms. Well, with dot products, it doesn't matter the order, so this is really just 2 of that. So I need to do that. How do I calculate the S1, S2 dot product? Well, that's going to be S1x, S2x, plus S1y, S2y, plus S1z, S2z. So we we go ahead and, yeah, now I'm out of time. we do this. And so here I did all of the work, and then I zoom in so we can see it clearly. So this is SX1, SX2, SY1, SY2, SZ1, SZ2. Don't ask me why the orange pen has suddenly become thinner. I don't know why. And so notice that minus I squared is minuses squared is plus, but I squared is minus. So this is negative. These are both down, so these add up to 0.
Right.
And so this here is all that remained there. So this is 1/4 times 2, 1/2. 3/4 plus 3/4 is 6/4, or 1 1/2. 1 1/2 plus 1 1/2 is 2. Yay. Yeah. Then if you do the plus minus, you get that. The minus plus, you get this. And then we're going to take and combine those. I'm totally out of time, so I'm not going to do it. We'll talk about Clebsch-Gordon next class period. So yeah, this was just repeating what I had before, and then Clebsch-Gordon stuff we'll talk about later.
Okay, sounds good.
See you Monday. Yeah, have a happy Sabbath.
Yep, you too.
Every day I have to stop and think what day of the week it is, in case you're wondering.